This is a photo taken of the night sky. A meteor and its tail are shown entering the Earth's atmosphere. Figure 3.1 meteor showers are rare, but the probability of them occurring can be calculated. Credit. Modification of work, a meteor during the peak of the 2009 Leonid meteor shower by Navicore/Wikimedia Commons. CC by 30, it is often necessary to guess about the outcome of an event in order to make a decision. Politicians study polls to guess their likelihood of winning an election. Teachers choose a particular course of study based on what they think students can comprehend. Doctors choose the treatments needed for various diseases based on their assessment of likely results. You may have visited a casino where people play games chosen because of the belief that the likelihood of winning is good. You may have chosen your course of study based on the probable availability of jobs. You have more than likely used probability. In fact, you probably have an intuitive sense of probability. Probability deals with the chance of an event occurring. Whenever you weigh the odds of whether or not to do your homework or to study for an exam, you are using probability. In this chapter, you will learn how to solve probability problems using a systematic approach. Probability is a measure that is associated with how certain we are of outcomes of a particular experiment or activity. An experiment is a planned operation carried out under controlled conditions. If the result is not predetermined, then the experiment is said to be a chance experiment. Flipping one fair coin twice is an example of an experiment. A result of an experiment is called an outcome. The sample space of an experiment is the set of all possible outcomes. Three ways to represent a sample space are to list the possible outcomes, to create a tree diagram, or to create a Venn diagram. The uppercase letter S is used to denote the sample space. For example, if you flip one fair coin, S equals HT, where H equals heads and T equals tails are the outcomes. An event is any combination of outcomes. Uppercase letters like A and B represent events. For example, if the experiment is to flip one fair coin, event A might be getting at most one head. The probability of an event A is written P, A's. The probability of any outcome is the long-term relative frequency of that outcome. Probabilities are between 0 and 1, inclusive, that is, 0 and 1 and all numbers between these values. PA equals 0 means the event A can never happen. PA equals 1 means the event A always happens. PA equals 0.5 means the event A is equally likely to occur or not to occur. For example, if you flip one fair coin repeatedly, from 20 to 2,000 to 20,000 times, the relative frequency of heads approaches 0. 5. The probability of heads. Equally likely means that each outcome of an experiment occurs with equal probability. For example, if you toss a fair six-sided die, each face 1, 2, 3, 4, 5, or 6 is as likely to occur as any other face. If you toss a fair coin, a head H and a tail T are equally likely to occur. If you randomly guess the answer to a true-false question on an exam, you are equally likely to select a correct answer or an incorrect answer. To calculate the probability of an event A when all outcomes in the sample space are equally likely, count the number of outcomes for event A and divide by the total number of outcomes in the sample space. For example, if you toss a fair dime and a fair nickel, the sample space is HH, TH, HT, TT, where T equals tails and H equals heads. The sample space has 4 outcomes, A equals getting 1 head. There are 2 outcomes that meet this condition, HT, TH, so PA equals 2, 4 equals 0, 5. Suppose you roll one fair six-sided die with the numbers 1, 2, 3, 4, 5, 6 on its faces. Let event E equals rolling a number that is at least 5. There are 2 outcomes, 5, 6, PE equals 2, 6. If you were to roll the die only a few times, you would not be surprised if your observed results did not match the probability. If you were to roll the die a very large number of times, you would expect that overall 2, 6 of the rolls would result in an outcome of at least 5. You would not expect exactly 2, 6. The long-term relative frequency of obtaining this result would approach the theoretical probability of 2, 6 as the number of repetitions grows larger and larger. This important characteristic of probability experiments is known as the law of large numbers, discussed in detail later, which states that as the number of repetitions of an experiment is increased, the relative frequency obtained in the experiment tends to become closer and closer to the theoretical probability. Even though the outcomes do not happen according to any set pattern or order overall, the long-term observed relative frequency will approach the theoretical probability. The word empirical is often used instead of the word observed. It is important to realize that in many situations the outcomes are not equally likely. A coin or die may be unfair or biased. 2 math professors in Europe had their statistics students test the Belgian €1 coin and discovered that in 250 trials, a head was obtained 56% of the time and a tail was obtained 44% of the time. The data seem to show that the coin is not a fair coin. More repetitions would be helpful to draw a more accurate conclusion about such bias. Some dice may be biased. Look at the dice in a game you have at home. The spots on each face are usually small holes carved out and then painted to make the spots visible. Your dice may or may not be biased. It is possible that the outcomes may be affected by the slight weight differences due to the different numbers of holes in the faces. Gambling casinos make a lot of money depending on outcomes from rolling dice, so casino dice are made differently to eliminate bias. Casino dice have flat faces. The holes are completely filled with paint having the same density as the material that the dice are made out of so that each face is equally likely to occur. Later, we will learn techniques to use to work with probabilities for events that are not equally likely. OR event, an outcome is in the event A or B if the outcome is in A or is in B or is in both A and B. The event A or B can also be written as a union B, with notation as follows. A letter 1D435 for example, let A equals 1, 2, 3, 4, 5 and B equals 4, 5, 6, 7, 8. Then A letter 1D435 equals 1, 2, 3, 4, 5, 6, 7, 8. Notice that 4 and 5 are not listed twice. And event, an outcome is in the event A and B if the outcome is in both A and B at the same time. The event A and B can also be written as the intersection B, with notation as follows. A for example, let A and B be 1, 2, 3, 4, 5 and 4, 5, 6, 7, 8 respectively. Then A letter 1D435 equals 4, 5. The complement of event A is denoted A read a prime. A consists of all outcomes that are not in A. Notice that PA plus PA equals 1. For example, let S equals 1, 2, 3, 4, 5, 6 and let A equals 1, 2, 3, 4. Then A equals 5, 6. PA equals 4, 6, PA equals 2, 6 and PA plus P. A equals 4, 6 plus 2, 6 equals 1. The conditional probability of a given B is written P of B. P of B is the probability that event A will occur given that the event B has already occurred. A conditional reduces the sample space. We calculate the probability of A from the reduced sample space B. The formula to calculate P of B is P of B equals letter 1D443, letter 1D434, letter 1D435, letter 1D443, letter 1D435, where PB is greater than 0. For example, suppose we toss one fair, six-sided die. The sample space S equals 1, 2, 3, 4, 5, 6. Let A equals faces 2 or 3 and B equals faces even 2, 4, 6. To calculate P of B, we count the number of outcomes 2 or 3 in the sample space B equals 2, 4, 6. Then we divide that by the number of outcomes B rather than S. We get the same result by using the formula. Remember that S has 6 outcomes. P of B equals letter 1D443, letter 1D434, letter 1D435, letter 1D443, letter 1D435, equals the number of outcomes or 3 and even in letter 1D446, 6, the number of outcomes even in letter 1D446. 6 equals 1636 equals 1 3 odds. The odds of an event presents the probability as a ratio of success to failure. This is common in various gambling formats. Mathematically, the odds of an event can be defined as letter 1D443, letter 1D434, 1 minus letter 1D443, letter 1D434, where PA is the probability of success and of course 1 minus PA is the probability of failure. Odds are always quoted as numerator to denominator, e.g. 2 to 1. Here the probability of winning is twice that of losing, thus the probability of winning is 0, 66, a probability of winning of 0. 60 would generate odds in favor of winning of 3 to 2. While the calculation of odds can be useful in gambling venues in determining payoff amounts, it is not helpful for understanding probability or statistical theory. Understanding terminology and symbols, it is important to read each problem carefully to think about and understand what the events are. Understanding the wording is the first very important step in solving probability problems. Reread the problem several times if necessary. Clearly identify the event of interest. Determine whether there is a condition stated in the wording that would indicate that the probability is conditional. Carefully identify the condition, if any. Example 3.1 problem. The sample space S is the whole numbers starting at 1 and less than 20. S equals let event A equals the even numbers and event B equals numbers greater than 13. A equals B equals PA equals PB equals a B equals a ORB equals PAB equals PAB equals A equals PA equals P A plus PA equals PAB equals PBA equals. Are the probabilities equal? Solution S equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. A equals 2, 4, 6, 8, 10, 12, 14, 16, 18. B equals 14, 15, 16, 17, 18, 19. P. A equals 9, 19. P. B equals 6, 19. A B equals 14, 16, 18. A OR B equals 2, 4, 6, 8, 10, 12. 14, 15, 16, 17, 18, 19 PAB equals 319 PAB equals 12, 19A equals 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. PA equals 10, 19 P, A plus P. A equals 1, 9, 19 plus 10, 19 equals 1 P A B equals letter 1 D4 4 3, letter 1 D4 3 4, letter 1 D4 3 5, letter 1 D4 4 3, letter 1 D4 3 5 equals 3 6. PBA equals letter 1 D4 4 3, letter 1 D4 3 4, letter 1 D4 3 5, letter 1 D4 4 3, letter 1 D4 3 4 equals 3 9. No, try it 3. 1. The sample space S is all the ordered pairs of two whole numbers, the first from 1 to 3 and the second from 1 to 4. Example 1, 4. S equals let event A equals the sum is even and event B equals the first number is prime. A equals B equals P A equals P B equals a B equals P A B equals P A B equals B equals P B equals P A plus P A equals P A B equals P B A equals. Are the probabilities equal? Example 3-2 problem. A fair six-sided die is rolled. Describe the sample space S, identify each of the following events with a subset of S and compute its probability. An outcome is the number of dots that show up. Event T equals the outcome is 2. Event A equals the outcome is an even number. Event B equals the outcome is less than 4. The complement of A B B a B A B A B. Event N equals the outcome is a prime number. Event I equals the outcome is 7. Solution T equals 2, P T equals 1 6 A equals 2 4 6 P A equals 1 2 B equals 1 2 3 P B equals 1 2 A equals 1 3 5. P A equals 1 2 A B equals 2 P A B equals 1 3 B A equals 2 P B A equals 1 3 A B equals 2 P A B equals 1 6 A B equals 1 2 3 4 6. PAB equals 5 6 AB equals 2 4 5 6 PAB equals 2 3 N equals 2 3 5 P N equals 1 2. A six-sided die does not have 7 dots. P7 equals 0. Try it 3 2. A number is randomly selected between 1 to 10. Describe the sample space S, identify each of the following events with a subset of S, and compute its probability. An outcome is the number selected. Event F equals the outcome is 5. Event A equals the number is more than 6. Event B equals the number is odd. The complement of BA given BB given AA or BA or B. Event P equals the outcome is a composite number. Event M equals the number is a multiple of 3. Example 3.3 Table 3.1 describes the distribution of a random sample S of 100 individuals, organized by sex assigned at birth and whether they are right or left-handed. Right-handed, left-handed males, 43.9 females, 44.4 Table 3.1 problem. Let's denote the events M equals the subject is male, F equals the subject is female, R equals the subject is right-handed, L equals the subject is left-handed. Compute the following probabilities. PM, PF, PR, PL, PMR, PF, L, PMF, PMR, PF, L, PM, PRM, PF, L, PLF. Solution PM equals 0. 52 PF equals 0. 48 PR equals 0. 87 PL equals 0. 13 PMR equals 0. 43 PFL equals 0. 4 PMF equals 1. PMR equals 0. 96 PFL equals 0. 57 PM equals 0. 48 PRM equals 0. 8269, rounded to 4 decimal places, PFL equals 0. 3077, rounded to 4 decimal places, PLF equals 0. 833. Try it 3. 3. The table describes the distribution of a random sample S of 100 individuals, organized by gender and whether they like tea or coffee. Tea coffee men 2226, women 1636. Table 3. 2. Let's denote the events M equals the subject is a man, W equals the subject is a woman, T equals the subject likes tea, and C equals the subject likes coffee. Compute the following probabilities. PM, PW, PT, PC, PM, and T, PW, and C, PM, or W, PM, or T, PW, or C, PM, PTM, PW, C, PCW. Independent and mutually exclusive do not mean the same thing. Independent events, two events are independent if one of the following are true. Letter 1 D4 4 3, letter 1 D4 3 4, letter 1 D4 3 5. Equals letter 1 D4 4 3, letter 1 D4 3 4, letter 1 D4 4 3, letter 1 D4 3 5, letter 1 D4 3 4. Equals letter 1 D4 4 3, letter 1 D4 3 5, letter 1 D4 4 3, letter 1 D4 3 4, letter 1 D4 3 5. Equals letter 1 D4 4 3, letter 1 D4 3 4, letter 1 D4 4 3, letter 1 D4 3 5. Two events A and B. Independent if the knowledge that one occurred does not affect the chance the other occurs. For example, the outcomes of two rolls of a fair die are independent events. The outcome of the first roll does not change the probability for the outcome of the second roll. To show two events are independent, you must show only one of the above conditions. If two events are not independent, then we say that they are dependent. Sampling may be done with replacement or without replacement. With replacement, if each member of a population is replaced after it is picked, then that member has the possibility of being chosen more than once. When sampling is done with replacement, then events are considered to be independent, meaning the result of the first pick will not change the probabilities for the second pick. Without replacement, when sampling is done without replacement, each member of a population may be chosen only once. In this case, the probabilities for the second pick are affected by the result of the first pick. The events are considered to be dependent or not independent. If it is not known whether A and B are independent or dependent, assume they are dependent until you can show otherwise. Example 3. For you have a fair, well-shuffled deck of 52 cards. It consists of 4 suits. The suits are clubs, diamonds, hearts, and spades. There are 13 cards in each suit consisting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, J, Jack, Q, Queen, K, King of that suit. A. Sampling with replacement. Suppose you pick 3 cards with replacement. The first card you pick out of the 52 cards is the Q of spades. You put this card back, reshuffle the cards, and pick a second card from the 52 card deck. It is the 10 of clubs. You put this card back, reshuffle the cards, and pick a third card from the 52 card deck. This time the card is the Q of spades again. Your picks are Q of spades, 10 of clubs, Q of spades. You have picked the Q of spades twice. You pick each card from the 52 card deck. Be sampling without replacement. Suppose you pick 3 cards without replacement. The first card you pick out of the 52 cards is the K of hearts. You put this card aside and pick the second card from the 51 cards remaining in the deck. It is the 3 of diamonds. You put this card aside and pick the third card from the remaining 50 cards in the deck. The third card is the J of spades. Your picks are K of hearts, 3 of diamonds, J of spades. Because you have picked the cards without replacement, you cannot pick the same card twice. The probability of picking the 3 of diamonds is called a conditional probability because it is conditioned on what was picked first. This is true also of the probability of picking the J of spades. The probability of picking the J of spades is actually conditioned on both the previous picks. Try at 3-4 you have a fair, well-shuffled deck of 52 cards. It consists of 4 suits. The suits are clubs, diamonds, hearts, and spades. There are 13 cards in each suit consisting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, J, Jack, Q, Queen, K, King of that suit. 3 cards are picked at random. Suppose you know that the picked cards are Q of spades, K of hearts, and Q of spades. Can you decide if the sampling was with or without replacement? Suppose you know that the picked cards are Q of spades, K of hearts, and J of spades. Can you decide if the sampling was with or without replacement? Example 3-5 problem. You have a fair, well-shuffled deck of 52 cards. It consists of 4 suits. The suits are clubs, diamonds, hearts, and spades. There are 13 cards in each suit consisting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, J, Jack, Q, Queen, and K, King of that suit. S equals spades, H equals hearts, D equals diamonds, C equals clubs. Suppose you pick 4 cards but do not put any cards back into the deck. Your cards are QS, 1D, 1C, QD. Suppose you pick 4 cards and put each card back before you pick the next card. Your cards are KH, 7D, 6D, KH. Which of A or B did you sample with replacement, and which did you sample without replacement? Solution: A without replacement. B with replacement. Try at 3-5 you have a fair, well-shuffled deck of 52 cards. It consists of 4 suits. The suits are clubs, diamonds, hearts, and spades. There are 13 cards in each suit consisting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, J, Jack, Q, Queen, and K, King of that suit. S equals spades, H equals hearts, D equals diamonds, C equals clubs. Suppose that you sample 4 cards without replacement. Which of the following outcomes are possible? Answer the same question for sampling with replacement. QS 1D 1C QD KH 7D 6D KH QS 7D 6D. K's mutually exclusive events A and B are mutually exclusive events if they cannot occur at the same time. Said another way, if occurred then B cannot occur and vice versa. This means that A and B do not share any outcomes in letter 1D443, letter 1D434, letter 1D435 equals 0. For example, suppose the sample space S equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let A equals 1, 2, 3, 4, 5, B equals 4, 5, 6, 7, 8, and C equals 7, 9. A B equals 4, 5, letter 1D443, letter 1D434, letter 1D435, 2, 10 and is not equal to 0. Therefore, A and B are not mutually exclusive. A and C do not have any numbers in common, so letter 1D443, letter 1D434 equals 0. Therefore, A and C are mutually exclusive. If it is not known whether A and B are mutually exclusive, assume they are not until you can show otherwise. The following examples illustrate these definitions and terms. Example 3, 6 flip 2 fair coins. This is an experiment. The sample space is HH, HT, TH, TT where T equals tails and H equals heads. The outcomes are HH, HT, TH, and TT. The outcomes HT and TH are different. The HT means that the first coin showed heads and the second coin showed tails. The TH means that the first coin showed tails and the second coin showed heads. Let A equals the event of getting at most one tail. At most one tail means 0 or one tail. Then it can be written as HH, HT, TH. The outcome HH shows 0 tails. HT and TH each show one tail. Let B equals the event of getting all tails. B can be written as TT. B is the complement of A, so B equals A. Also, PA plus PB equals P. A, PA equals 1. The probabilities for A and for B are P. A equals 3, 4, and PB equals 1, 4. Let C equals the event of getting all heads. C equals HH. Since B equals TT, letter 1 D443, letter 1 D435, letter 1 D436 equals 0, B and C are mutually exclusive. B and C have no members in common because you cannot have all tails and all heads at the same time. Let D equals event of getting more than one tail, D equals TT. PD equals 1, 4. Let E equals event of getting a head on the first roll. This implies you can get either a head or tail on the second roll. E equals HT, PE equals 2, 4. Find the probability of getting at least one or two tail and two flips. Let F equals event of getting at least one tail and two flips. F equals HT, TH, TT. PF equals 3, 4. Try at 3, 6. Draw two cards from a standard 52 card deck with replacement. Find the probability of getting at least one black card. Example 3-7 problem. Flip two fair coins. Find the probabilities of the events. Let F equals the event of getting at most one tail, 0 or one tail. Let G equals the event of getting two faces that are the same. Let H equals the event of getting a head on the first flip followed by a head or tail on the second flip. Are F and G mutually exclusive? Let J equals the event of getting all tails. Are J and H mutually exclusive? Solution. Look at the sample space in example 3600, or 1 tails occur when the outcomes HH, TH, HT show up. PF equals 3, 4. Two faces are the same if HH or TT show up. PG equals 2, 4. A head on the first flip followed by a head or tail on the second flip occurs when HH or HT show up. PH 2, 4. F and G share HH, so letter 1 D43A is not equal to 0, 0. F and G are not mutually exclusive. Getting all tails occurs when tails shows up on both coins TT. H's outcomes are HH and HT. J and H have nothing in common, so letter 1 D443, letter 1 D43D equals 0. J and H are mutually exclusive. Try at 3. 7. A box has two balls, one white and one red. We select one ball, put it back in the box, and select a second ball, sampling with replacement. Find the probability of the following events. Let F equals the event of getting the white ball twice. Let G equals the event of getting two balls of different colors. Let H equals the event of getting white on the first pick. Are F and G mutually exclusive? Are G and H mutually exclusive? Example 3, 8. Roll one fair, six-sided die. The sample space is 1, 2, 3, 4, 5, 6. Let event A equals a face is odd. Then A equals 1, 3, 5. Let event B equals a face is even. Then B equals 2, 4, 6. Find the complement of AA. The complement of AA is B because A and B together make up the sample space. PA plus PB equals PA, PA equals 1. Also PA equals 3, 6 and PB equals 3, 6. Let event C equals odd faces larger than 2. Then C equals 3, 5. Let event D equals all even faces smaller than 5. Then D equals 2, 4. Letter 1 D437 equals 0 because you cannot have an odd and even face at the same time. Therefore, C and D are mutually exclusive events. Let event E equals all faces less than 5. E equals 1, 2, 3, 4. Problem. Are C and E mutually exclusive events? Answer yes or no. Why or why not? Solution. No. C equals 3, 5 and E equals 1, 2, 3, 4. Letter 1 D443, letter 1 D436, letter 1 D438, 1, 6. To be mutually exclusive, letter 1 D438 must be 0. Find letter 1 D443, letter 1 D436, letter 1 D434. This is a conditional probability. Recall that the event C is 3, 5 and event A is 1, 3, 5. To find letter 1 D443, letter 1 D436, letter 1 D434, find the probability of C using the sample space A. You have reduced the sample space from the original sample space, 1, 2, 3, 4, 5, 6 to 1, 3, 5. So letter 1 D443, letter 1 D436, letter 1 D434 equals 2, 3. Try at 3, 8. Let event A equals learning Spanish. Let event B equals learning German. Then A letter 1 D435 equals learning Spanish and German. Suppose letter 1 D443, letter 1 D434 equals 0, 4 and letter 1 D443, letter 1 D435 equals 0, 2. Letter 1 D443, letter 1 D434, letter 1 D435 equals 0. 8. Are events A and B independent? Hint, you must show one of the following. Letter 1 D443, letter 1 D434, letter 1 D435. Equals letter 1 D443, letter 1 D434, letter 1 D443, letter 1 D435, letter 1 D434. Equals letter 1 D443, letter 1 D435, letter 1 D443, letter 1 D434, letter 1 D435. Equals letter 1 D443, letter 1 D434, letter 1 D443, letter 1 D435. Example 3. 9. Let event G equals taking a math class. Let event H equals taking a science class. Then GH equals taking a math class and a science class. Suppose letter 1 D443, letter 1 D43A equals 0. 6. Letter 1 D443, letter 1 D43B equals 0. 5. And letter 1 D43B equals 0. 3. Are G and H independent? If G and H are independent, then you must show one of the following. Letter 1 D443, letter 1 D43A, letter 1 D43B. Equals letter 1 D443, letter 1 D43A, letter 1 D443, letter 1 D43B, letter 1 D43A, equals letter 1 D443, letter 1 D43B, letter 1 D443, letter 1 D43A, equals letter 1 D443, letter 1 D43A, letter 1 D443, letter 1 D43B. Note the choice you make depends on the information you have. You could choose any of the methods here because you have the necessary information. Problem A, show that letter 1 D443, letter 1 D43A, letter 1 D43B equals letter 1 D443, letter 1 D43A. Solution: letter 1 D443, letter 1 D43A, letter 1 D43B equals letter 1 D443, letter 1 D43A, letter 1 D443, letter 1 D43B equals 0. 305 equals 0. 6 equals letter 1 D443, letter 1 D43A. Problem B, show letter 1 D443, letter 1 D43A equals letter 1 D443, letter 1 D43A, letter 1 D443, letter 1 D43B. Solution: letter 1 D443, letter 1 D43A, letter 1 D443, letter 1 D43B equals 0. 6, 0, 5 equals 0. 3 equals letter 1 D443, letter 1 D43A. Since G and H are independent, knowing that a person is taking a science class does not change the chance that they are taking a math class. If the two events had not been independent, that is, they are dependent, then knowing that a person is taking a science class would change the chance they are taking math. For practice, show that letter 1 D443, letter 1 D43B, letter 1 D43A equals letter 1 D443, letter 1 D43B to show that G and H are independent events. Try it. 3. 9. In a bag there are 6 red marbles and 4 green marbles. The red marbles are marked with the numbers 1, 2, 3, 4, 5, and 6. The green marbles are marked with the numbers 1, 2, 3, and 4. R equals a red marble, G equals a green marble, O equals an odd-numbered marble. The sample space is S equals R1, R2, R3, R4, R5, R6, G1, G2, G3, G4. S has 10 outcomes. What is letter 1 D443, letter 1 D43A, letter 1 D442? Example 310 problem: let event C equals taking an English class. Let event D equals taking a speech class. Suppose letter 1 D443, letter 1 D436 equals 0. 75, letter 1 D443, letter 1 D437 equals 0. 3. Letter 1 D443, letter 1 D436, letter 1 D437 equals 0. 75 and equals 0. 225. Justify your answers to the following questions numerically. Are C and D independent? Are C and D mutually exclusive? What is letter 1 D443, letter 1 D437, letter 1 D436? Solution: yes, because letter 1 D443, letter 1 D436, letter 1 D437 equals letter 1 D443, letter 1 D436. No, because is not equal to 0. Letter 1 D443, letter 1 D437, letter 1 D436 equals letter 1 D443, letter 1 D436, letter 1 D437, letter 1 D443, letter 1 D436 equals 0. 225. 0. 75 equals 0. 3. Try it. 3. 10. A student goes to the library. Let events B equals the student checks out a book and D equals the student checks out a DVD. Suppose that letter 1 D443, letter 1 D435 equals 0. 40. Letter 1 D443, letter 1 D437 equals 0. 30. And letter 1 D443, letter 1 D435, letter 1 D437 equals 0. 20. Find letter 1 D443, letter 1 D435, letter 1 D437. Find letter 1 D443, letter 1 D437, letter 1 D435. Are B and D independent? Are B and D mutually exclusive? Example 3. 11. In a box there are 3 red cards and 5 blue cards. The red cards are marked with the numbers 1, 2, and 3, and the blue cards are marked with the numbers 1, 2, 3, 4, and 5. The cards are well shuffled. You reach into the box you cannot see into it and draw one card. Let R equals red card is drawn, B equals blue card is drawn, E equals even numbered card is drawn. The sample space S equals R1, R2, R3, B1, B2, B3, B4, B5. S has 8 outcomes. Letter 1 D443, letter 1 D445 equals 38. Letter 1 D443, letter 1 D435 equals 58. Letter 1 D443, letter 1 D445, letter 1 D435 equals 0. You cannot draw one card that is both red and blue. Letter 1 D443, letter 1 D438 equals 38. There are 3 even-numbered cards R2, B2, and B4. Letter 1 D443, letter 1 D438, letter 1 D435 equals 25. There are 5 blue cards B1, B2, B3, B4, and B5. Out of the blue cards there are 2 even cards B2 and B4. Letter 1 D443, letter 1 D435, letter 1 D438 equals 23. There are 3 even-numbered cards R2, B2, and B4. Out of the even-numbered cards 2 are blue B2 and B4. The events R and B are mutually exclusive because letter 1 D443, letter 1 D445, letter 1 D435 equals 0. Let G equals card with a number greater than 3. G equals B4, B5, letter 1 D443, letter 1 D43A equals 28. Let H equals blue card numbered between 1 and 4 inclusive. H equals B1, B2, B3, B4, letter 1 D443, letter 1 D43A, letter 1 D43B equals 1, 4. The only card in H that has a number greater than 3 is B4. Since 28 equals 1, 4, letter 1 D443, letter 1 D43A equals letter 1 D443, letter 1 D43A, letter 1 D43B, which means that G and H are independent. Try at 311 in a basketball arena, 70% of the fans are rooting for the home team. 25% of the fans are wearing blue. 20% of the fans are wearing blue and are rooting for the away team. Of the fans rooting for the away team, 67% are wearing blue. Let A be the event that a fan is rooting for the away team. Let B be the event that a fan is wearing blue. Are the events of rooting for the away team and wearing blue independent? Are they mutually exclusive? Example 312. In a particular college class, 60% of the students are female. 50% of all students in the class have long hair. 45% of the students are female and have long hair. Of the female students, 75% have long hair. Let F be the event that a student is female. Let L be the event that a student has long hair. One student is picked randomly. Are the events of being female and having long hair independent? The following probabilities are given in this example. Letter 1 D443, letter 1 D439 equals 0. 60, letter 1 D443, letter 1 D43F equals 0. 50, letter 1 D443, letter 1 D439 equals 0. 45, letter 1 D443, letter 1 D43F, letter 1 D439 equals 0. 75. Note the choice you make depends on the information you have. You could use the first or last condition on the list for this example. You do not know PFL yet, so you cannot use the second condition. Check whether letter 1 D443, letter 1 D439, letter 1 D43F equals letter 1 D443, letter 1 D439, letter 1 D443, letter 1 D43F. We are given that equals 0. 45, but letter 1 D443, letter 1 D439, letter 1 D443, letter 1 D43F equals 0. 60, 0, 50 equals 0, 30. The events of being female and having long hair are not independent because letter 1 D443, letter 1 D439, letter 1 D43F does not equal letter 1 D443, letter 1 D439, letter 1 D443, letter 1 D43F. Check whether letter 1 D443, letter 1 D43F, letter 1 D439 equals letter 1 D443, letter 1 D43F. We are given that letter 1 D443, letter 1 D43F, letter 1 D439 equals 0. 75, but letter 1 D443, letter 1 D43F equals 0. 50, they are not equal. The events of being female and having long hair are not independent. Interpretation of results. The events of being female and having long hair are not independent. Knowing that a student is female changes the probability that a student has long hair. Try at 312. Mark is deciding which route to take to work. His choices are I equals the interstate and F equals 5th Street. Letter 1 D443, letter 1 D43C equals 0. 44 and letter 1 D443, letter 1 D439 equals 0. 56, letter 1 D443, letter 1 D43C equals 0 because Mark will take only one route to work. What is the probability of letter 1 D443, letter 1 D43C, letter 1 D439? Example 313 problem. Toss one fair coin. The coin has two sides, H and T. The outcomes are count the outcomes. There are outcomes. Toss one fair six-sided die. The die has 1, 2, 3, 4, 5 or 6 dots on a side. The outcomes are count the outcomes. There are outcomes. Multiply the two numbers of outcomes. The answer is if you flip one fair coin and follow it with the toss of one fair six-sided die, the answer to C is the number of outcomes, size of the sample space. What are the outcomes? Hint, two of the outcomes are H1 and T6. Event A equals heads H on the coin followed by an even number 2, 4, 6 on the die. A equals find P A. Event B equals heads on the coin followed by a 3 on the die. B equals find PB. Are A and B mutually exclusive? Hint, what is letter 1 D443, letter 1 D434, letter 1 D435? If letter 1 D443, letter 1 D434, letter 1 D435 equals 0, then A and B are mutually exclusive. Are A and B independent? Hint. Is letter 1 D443, letter 1 D434, letter 1 D435 equals letter 1 D443, letter 1 D434, letter 1 D443, letter 1 D435? If letter 1 D443, letter 1 D434, letter 1 D435 equals letter 1 D443, letter 1 D434, letter 1 D443, letter 1 D435, then A and B are independent. If not, then they are dependent. Try at 313. A box has two balls, one white and one red. We select one ball, put it back in the box, and select a second ball, sampling with replacement. Let T be the event of getting the white ball twice, F the event of picking the white ball first, S the event of picking the white ball in the second drawing. Compute letter 1 D443, letter 1 D447. Compute letter 1 D443, letter 1 D447, letter 1 D439. Are T and F independent? Are F and S mutually exclusive? Are F and S independent? When calculating probability, there are two rules to consider when determining if two events are independent or dependent, and if they are mutually exclusive or not. The multiplication rule: if A and B are two events defined on a sample space, then letter 1 D443, letter 1 D434, letter 1 D435 equals letter 1 D443, letter 1 D435, letter 1 D443, letter 1 D434, letter 1 D435. We can think of the intersection symbol as substituting for the word, and this rule may also be written as letter 1 D443, letter 1 D434, letter 1 D435 equals letter 1 D443, letter 1 D434, letter 1 D435, letter 1 D443, letter 1 D435. This equation is read as the probability of a given B equals the probability of A and B divided by the probability of B. If A and B are independent, then letter 1 D443, letter 1 D434, letter 1 D435 equals letter 1 D443, letter 1 D434. Then letter 1 D443, letter 1 D434, letter 1 D435 equals letter 1 D443, letter 1 D434, letter 1 D435, letter 1 D443, letter 1 D435 becomes letter 1 D443, letter 1 D434, letter 1 D435 equals letter 1 D443, letter 1 D434. Letter 1 D435 because the letter 1 D443, letter 1 D434, letter 1 D435 equals letter 1 D443, letter 1 D434 if A and B are independent. One easy way to remember the multiplication rule is that the word "and" means that the event has to satisfy two conditions. For example, the name drawn from the class roster is to be both a woman and a sophomore. It is harder to satisfy two conditions than only one, and of course, when we multiply fractions, the result is always smaller. This reflects the increasing difficulty of satisfying two conditions. The addition rule: if A and B are defined on a sample space, then letter 1 D443, letter 1 D434, letter 1 D435 equals letter 1 D443, letter 1 D434, letter 1 D443, letter 1 D435 minus letter 1 D443, letter 1 D434, letter 1 D435. We can think of the union symbol substituting for the word, or the reason we subtract the intersection of A and B is to keep from double counting elements that are in both A and B. If A and B are mutually exclusive, then letter 1 D443, letter 1 D434, letter 1 D435 equals 0. Then letter 1 D443, letter 1 D434, letter 1 D435 equals letter 1 D443, letter 1 D434, letter 1 D443, letter 1 D435 minus letter 1 D443, letter 1 D434, letter 1 D435 becomes letter 1 D443, letter 1 D434, letter 1 D435 equals letter 1 D443, letter 1 D434, letter 1 D443, letter 1 D435. Example 3, 14. Klaus is trying to choose where to go on vacation. His two choices are A equals New Zealand and B equals Alaska. Klaus can only afford one vacation. The probability that he chooses A is P. A equals 0.6 and the probability that he chooses B is P. B equals 0.35. Letter 1 D443, letter 1 D434, letter 1 D435 equals 0 because Klaus can only afford to take one vacation. Therefore, the probability that he chooses either New Zealand or Alaska is letter 1 D443, letter 1 D434, letter 1 D435 equals letter 1 D443, letter 1 D434, letter 1 D443, letter 1 D435 equals 0. 6 plus 0.35 equals 0.95. Note that the probability that he does not choose to go anywhere on vacation must be 0. 5. Try at 3. 14. Anna has to buy a new car. She has two choices, car A and car B. Anna can afford only one car. The probability that Anna will buy car A is letter 1d443, letter 1d434 equals 0. 25 and the probability that Anna will buy car B is letter 1d443, letter 1d435 equals 0. 65. Find letter 1d443, letter 1d434, letter 1d434, letter 1d441, letter 1d437b, letter 1d443, letter 1d434, letter 1d442, letter 1d445b. Example 3. 15 Carlos plays college soccer. He makes a goal 65% of the time he shoots. Carlos is going to attempt 2 goals in a row in the next game. A equals the event Carlos is successful on his first attempt. PA equals 0.65. B equals the event Carlos is successful on his second attempt. PB equals 0.65. Carlos tends to shoot in streaks. The probability that he makes the second goal that he made the first goal is 0.90. Problem: what is the probability that he makes both goals? What is the probability that Carlos makes either the first goal or the second goal? Are A and B independent? Are A and B mutually exclusive? Solution A. The problem is asking you to find letter 1d443, letter 1d434, letter 1d435 equals letter 1d443, letter 1d435, letter 1d434. Since PBA equals 0.90, PBA equals PBA, PA equals 0, 90, 0. 65 equals 0. 585 Carlos makes the first and second goals with probability 0. 585b. The problem is asking you to find PAB. PAB equals PA plus PB. PAB equals 0. 65 plus 0. 65 0. 585 equals 0. 715 Carlos makes either the first goal or the second goal with probability 0. 715. See, no, they are not because PBA equals 0. 585, PBPA equals 0, 65, 0. 65 equals 0, 423, 0. 423 not equal to 0. 585 equals PBA, so PBA is not equal to PBPA. D, no, they are not because PAB equals 0, 585. To be mutually exclusive, PAB must equal 0. Try at 3:15. Helen plays basketball. For free throws, she makes the shot 75% of the time. Helen must now attempt 2 free throws. C equals the event that Helen makes the first shot. PC equals 0.75. D equals the event Helen makes the second shot. PD equals 0.75. The probability that Helen makes the second free throw given that she made the first is 0.85. What is the probability that Helen makes both free throws? Example 3. 16. A community swim team has 150 members. 75 of the members are advanced swimmers. 47 of the members are intermediate swimmers. The remainder are novice swimmers. 40 of the advanced swimmers practice 4 times a week. 30 of the intermediate swimmers practice 4 times a week. 10 of the novice swimmers practice 4 times a week. Suppose one member of the swim team is chosen randomly. Problem: what is the probability that the member is a novice swimmer? What is the probability that the member practices 4 times a week? What is the probability that the member is an advanced swimmer and practices 4 times a week? What is the probability that a member is an advanced swimmer and an intermediate swimmer? Are being an advanced swimmer and an intermediate swimmer mutually exclusive? Why or why not? Are being a novice swimmer and practicing 4 times a week independent events? Why or why not? Solution: 28, 150, 80, 150, 40, 150p advanced intermediate equals 0, so these are mutually exclusive events. A swimmer cannot be an advanced swimmer and an intermediate swimmer at the same time. No, these are not independent events. P novice practices 4 times per week equals 0. 667 P novice P practices 4 times per week equals 0.9960. 667 not equal to 0.996. Try at 3. 16. A school has 200 seniors of whom 140 will be going to college next year. 40 will be going directly to work. The remainder are taking a gap year. 50 of the seniors going to college play sports. 30 of the seniors going directly to work play sports. 5 of the seniors taking a gap year play sports. What is the probability that a senior is taking a gap year? Example 3:17. Felicity attends Modesto JC in Modesto, CA. The probability that Felicity enrolls in a math class is 0.2, and the probability that she enrolls in a speech class is 0.65. The probability that she enrolls in a math class that she enrolls in speech class is 0.25. Let M equals math class, S equals speech class, MS equals math. Given speech problem, what is the probability that Felicity enrolls in math and speech? Find PMS, PMSPS. What is the probability that Felicity enrolls in math or speech classes? Find PMS equals PM plus PS, PMS. Are M and S independent? Is PMS equals PM, are M and S mutually exclusive? Is PMS equals 0? Solution A0 1625, B0 6875, C no, D no, try it 3. 17. A student goes to the library. Let events B equals the student checks out a book and D equals the student checks out a DVD. Suppose that PB equals 0, 40, PD equals 0. 30 and PDB equals 0, 5. Find PBD, find PBD. Example 3:18 studies show that about 1 woman in 7, approximately 14.3% who live to be 90 will develop breast cancer. Suppose that of those women who develop breast cancer, a test is negative 2% of the time. Also suppose that in the general population of women, the test for breast cancer is negative about 85% of the time. Let B equals woman develops breast cancer and let N equals tests negative. Suppose one woman is selected at random. Problem: what is the probability that the woman develops breast cancer? What is the probability that woman tests negative? Given that the woman has breast cancer, what is the probability that she tests negative? What is the probability that the woman has breast cancer and tests negative? What is the probability that the woman has breast cancer or tests negative? Are having breast cancer and testing negative independent events? Are having breast cancer and testing negative mutually exclusive? Solution: PB equals 0, 143, PN equals 0. 85 PNB equals 0, 2 PBN equals PB, PNB equals 0. 143, 0. 2 equals 0, 29 PBN equals PB plus PN, PBN equals 0, 143 plus 0, 85, 0. 29 equals 0, 99, 01 number PN equals 0, 85, PNB equals 0, 2, so PNB does not equal PN, number PBN equals 0. 29, for B and N to be mutually exclusive, PBN must be 0, try it 3. 18. A school has 200 seniors of whom 140 will be going to college next year. 40 will be going directly to work. The remainder are taking a gap year. 50 of the seniors going to college play sports. 30 of the seniors going directly to work play sports. 5 of the seniors taking a gap year play sports. What is the probability that a senior is going to college and plays sports? Example 319 problem: refer to the information in example 318. P equals tests positive. Given that a woman develops breast cancer, what is the probability that she tests positive? Find PPB equals 1 PNB. What is the probability that a woman develops breast cancer and tests positive? Find PBP equals PPB. What is the probability that a woman does not develop breast cancer? Find PB equals 1 PB. What is the probability that a woman tests positive for breast cancer? Find PP equals 1 PN. Solution: A0 98, B0 1401, C0. 857, D0 15, try it 3. 19. A student goes to the library. Let events B equals the student checks out a book and D equals the student checks out a DVD. Suppose that PB equals 0, 40, PD equals 0, 30, and PDB equals 0, 5. Find PB, find PDB, find PBD, find PDB, find PDB. Contingency tables: a contingency table provides a way of portraying data that can facilitate calculating probabilities. The table helps in determining conditional probabilities quite easily. The table displays sample values in relation to two different variables that may be dependent or contingent on one another. Later on, we will use contingency tables again, but in another manner. Example 3. 20. Suppose a study of speeding violations and drivers who use cell phones produced the following fictional data. Speeding violation in the last year, no speeding violation in the last year total, uses cell phone while driving 25 280 305. Does not use cell phone while driving 45 405 450 total 7680 5 755 table 3. 3. The total number of people in the sample is 755. The row totals are 305 and 450. The column totals are 70 and 685. Notice that 305 plus 450 equals 755 and 70 plus 685 equals 755. Calculate the following probabilities using the table. Problem: find P driver is a cell phone user. Find P driver had no violation in the last year. Find P driver had no violation in the last year was a cell phone user. Find P driver is a cell phone user. Driver had no violation in the last year. Find P driver is a cell phone user. Driver had a violation in the last year. Find P driver had no violation last year. Driver was not a cell phone user. Solution: number of cell phone users total number in study equals 305 755 number that had no violation total number in study equals 685 755 280 755. 305 755 plus 685 755 minus 280. 755 equals 710, 755, 25, 70. The sample space is reduced to the number of drivers who had a violation. 405, 450, the sample space is reduced to the number of drivers who were not cell phone users. Try it 320 table 3. 4 shows the number of athletes who stretch before exercising and how many had injuries within the past year. Injury in last year, no injury in last year, total stretches 55, 295, 350, does not stretch 231, 219, 450 total, 286, 514, 800 table 3. 4. What is P athlete stretches before exercising? What is P athlete stretches before exercising, no injury in the last year? Example 321 table 3. 5 shows a random sample of 100 hikers and the areas of hiking they prefer. Sex the coastline near lakes and streams on mountain peaks, total women 18, 16, 45 men, 14, 55 total 41, table 3. 5 hiking area preference problem A, complete the table. Solution A, sex the coastline near lakes and streams on mountain peaks, total women 18, 16, 11, 45 men, 16, 25, 14, 55 total 34, 41, 25, 100 table 3. 6 hiking area preference problem B are the events being a woman and preferring the coastline independent events. Let F equals being a woman and let C equals preferring the coastline. Find letter 1 D443, letter 1 D439, letter 1 D436. Find P, F, P, C. Are these two numbers the same? If they are, then F and C are independent. If they are not, then F and C are not independent. Solution B, letter 1 D443, letter 1 D439, letter 1 D436 equals 18 100 equals 0. 18 PFPC equals 45 100, 34 100 equals 0, 45 0, 34 equals 0, 153 letter 1 D443, letter 1 D439, letter 1 D436 not equal to PFPC, so the events F and C are not independent. Problem C, find the probability that a person is a man given that the person prefers hiking near lakes and streams. Let M equals being a man, and let L equals prefers hiking near lakes and streams. What word tells you this is a conditional? Fill in the blanks and calculate the probability. P equals, is the sample space for this problem all 100 hikers? If not, what is it? Solution C. The word given tells you that this is a conditional. PML equals 2541. No, the sample space for this problem is the 41 hikers who prefer lakes and streams. Problem D. Find the probability that a person is a woman or prefers hiking on mountain peaks. Let F equals being a woman and let P equals prefers mountain peaks. Find P, F, find P, P. Find letter 1 D443. Find letter 1 D443, letter 1 D439, letter 1 D443. Solution D. PF equals 45 100 PP equals 25 100 letter 1 D443, letter 1 D439, letter 1 D443 equals 11 100 letter 1 D443, letter 1 D439, letter 1 D443 equals 45 100 plus 25 100 11 100 equals 59 100. Try it 3. 21 table 3 7 shows a random sample of 200 cyclists and the routes they prefer. Let O equals older and H equals hilly path. Age group lake path, hilly path, wooded path, total younger 45 38 27 110 older 26 52 12 90 total 71 90 39 200 table 3. 7 out of the older group, what is the probability that the cyclist prefers a hilly path? Are the events being older and preferring the hilly path independent events? Example 3. 22 Muddy Mouse lives in a cage with 3 doors. If Muddy goes out the first door, the probability that he gets caught by Alyssa the cat is 1/5, and the probability he is not caught is 4/5. If he goes out the second door, the probability he gets caught by Alyssa is 1/4, and the probability he is not caught is 3/4. The probability that Alyssa catches Muddy coming out of the third door is 1/2, and the probability she does not catch Muddy is 1/2. It is equally likely that Muddy will choose any of the 3 doors, so the probability of choosing each door is 1/3. Caught or not door 1 door 2 door 3 total, caught 115 112 16, not caught 415 312 16 total, 1 table 3. 8 door choice, the first entry 115 equals 15 13 is letter 1 D443, door 1 caught, the entry 415 equals 4513 is letter 1 D443, door 1 not caught, verify the remaining entries. Problem A, complete the probability contingency table. Calculate the entries for the totals. Verify that the lower right corner entry is 1. Solution A, caught or not door 1 door 2 door 3 total, caught 115 112 16 1960, not caught 415 312 16 40 160 total, 515 412 26 1 table 3. 9 door choice problem B. What is the probability that Alyssa does not catch Muddy? Solution B, 40 160. Problem C, what is the probability that Muddy chooses door 1 door 2 given that Muddy is caught by Alyssa? Solution C919. Try it 3. 22. Fred's preference to drink coffee or iced tea depends on the season. When it is summer, Fred's preference to drink coffee is 1-4 and his preference to drink iced tea is 3-4. When it is rainy season, Fred's preference to drink coffee is 1-2 and his preference to drink iced tea is 1-2. When it is winter, Fred's preference to drink coffee is 1-5 and his preference to drink iced tea is 1-5. A day randomly selected in a year has a probability of 1-3 for each season. The event here is selection of a day randomly in a year. Season summer, rainy, winter. Total coffee 112 164 15, iced tea 14 161 15, total 1 table 3. 10. The first entry is 1413 equals 112. The second entry is 3413 equals 14. Verify the remaining entries. Complete the probability contingency table. Calculate the entries for the totals. Verify that the lower right corner entry is 1. What is the probability that Fred will drink iced tea? What is the probability that the day is in summer or rainy season given that Fred drinks iced tea? Example 323. Table 311 contains the number of crimes per 100,000 inhabitants in the United States over the span of several years. Year: robbery, burglary, vandalism. Vehicle: total 145, 7 732, 129, 7 314, 7 2 133, 1 717. 729, 1 259, 2 3 119, 3 700 127, 7 239, 1 4 113, 7 702, 226. 8 229. 6. Total. Table 311. United States Crime Index rates per 100,000 inhabitants. Problem: total, each column and each row. Total data equals 4,520. 7. Find P year 2 and robbery. Find P year 3 and burglary. Find P year 3 or burglary. Find P year 4 vandalism. Find P vehicle year 1. Solution: A0. 294, B0 1551, C0 7165, D0 2365, E0 2575. Try it 323. Table 3. 12 relates the weights and heights of a group of individuals participating in an observational study. Weight: height, tall, medium, short. Totals: overweight 18 28 14, typical weight range 20 51 28, underweight 12 25 9. Totals. Table 3. 12. Find the total for each row and column. Find the probability that a randomly chosen individual from this group is tall. Find the probability that a randomly chosen individual from this group is overweight and tall. Find the probability that a randomly chosen individual from this group is tall given that the individual is overweight. Find the probability that a randomly chosen individual from this group is overweight given that the individual is tall. Find the probability a randomly chosen individual from this group is tall and underweight. Are the events overweight and tall independent? Tree diagrams. Sometimes, when the probability problems are complex, it can be helpful to graph the situation. Tree diagrams can be used to visualize and solve conditional probabilities. Tree diagrams. A tree diagram is a special type of graph used to determine the outcomes of an experiment. It consists of branches that are labeled with either frequencies or probabilities. Tree diagrams can make some probability problems easier to visualize and solve. The following example illustrates how to use a tree diagram. Example 324. In an urn there are 11 balls. 3 balls are red R and 8 balls are blue B. Draw 2 balls one at a time with replacement. With replacement means that you put the first ball back in the urn before you select the second ball. The tree diagram using frequencies that show all the possible outcomes follows. This is a tree diagram with branches showing frequencies of each draw. The first branch shows 2 lines, 8B and R. The second branch has a set of 2 lines, 8B and 3R for each line of the first branch. Multiply along each line to find 64BB, 24BR, 24RB, and 9RR. Figure 3:2. Total equals 64 plus 24 plus 24 plus 9 equals 121. The first set of branches represents the first draw. The second set of branches represents the second draw. Each of the outcomes is distinct. In fact, we can list each red ball as R1, R2, and R3 and each blue ball as B1, B2, B3, B4, B5, B6, B7, and B8. Then the 9RR outcomes can be written as R1, 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 R2, R1, R3, R2, R1, R2, 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 R3, R3, R1, R3, R2. R3, R3. The other outcomes are similar. There are a total of 11 balls in the urn. Draw 2 balls one at a time with replacement. There are 11 equals 121 outcomes, the size of the sample space. Problem A. List the 24 BR outcomes. B1R1, B1R2, B1R3. Solution A. B1R1, B1R2, B1R3, B2R1, B2R2. B2R3, B3R1, B3R2, B3R3, B4R1, B4R2, B4R3, B5R1, B5R2, B5R3, B6R1. B6R2, B6R3, B7R1, B7R2, B7R3, B8R1, B8R2, B8R3. Problem B. Using the tree diagram, calculate PRR. Solution B. PRR equals 311, 311 equals 9, 121. Problem C. Using the tree diagram, calculate letter 1 D443, letter 1 D445, letter 1 D435, letter 1 D435, letter 1 D445. Solution C. Letter 1 D443, letter 1D445, letter 1D435, letter 1D435, letter 1D445. 311, 811 plus 811 is 311 equals 48, 121. Problem D. Using the tree diagram, calculate letter 1D443, letter 1D445 on 1ST. Draw letter 1D435 on ND. Draw. Solution D. Letter 1D443, letter 1D445 on 1ST. Draw letter 1D435 on ND. Draw. 311, 811 equals 24, 121. Problem E. Using the tree diagram, calculate PR on second draw, B on first draw. Solution E. PR on second draw, B on first draw equals PR on second, B on first. 2488 equals 311. This problem is a conditional one. The sample space has been reduced to those outcomes that already have a blue on the first draw. There are 24 plus 64 equals 88 possible outcomes, 24 BR and 64 BB. 24 of the 88 possible outcomes are BR. 2488 equals 311. Problem F. Using the tree diagram, calculate PBB. Solution F. PBB equals 64, 121. Problem G. Using the tree diagram, calculate PB on the second draw, R on the first draw. Solution G. PB on second draw, R on first draw equals 811. There are 9 plus 24 outcomes that have R on the first draw, 9 RR and 24 RB. The sample space is then 9 plus 24 equals 33. 24 of the 33 outcomes have B on the second draw. The probability is then 2433. Try it 3. 24 in a standard deck. There are 52 cards. 12 cards are face cards, event F, and 40 cards are not face cards, event N. Draw 2 cards one at a time with replacement. All possible outcomes are shown in the tree diagram as frequencies. Using the tree diagram, calculate PFF. This is a tree diagram with branches showing frequencies of each draw. The first branch shows 2 lines. 12F and 40N. The second branch has a set of 2 lines, 12F and 40N, for each line of the first branch. Multiply along each line to find 144 FF, 480 FN, 480 NF, and 1600 NN. Figure 3.3. Example 325. An urn has 3 red marbles and 8 blue marbles in it. Draw 2 marbles, one at a time, this time without replacement from the urn. Without replacement means that you do not put the first ball back before you select the second marble. Following is a tree diagram for this situation. The branches are labeled with probabilities instead of frequencies. The numbers at the ends of the branches are calculated by multiplying the numbers on the 2 corresponding branches. For example, 311, 210 equals 6110. This is a tree diagram with branches showing probabilities of each draw. The first branch shows 2 lines, B811 and R311. The second branch has a set of 2 lines for each first branch line. Below B811 are B710 and R310. Below R311 are B810 and R210. Multiply along each line to find BB56110, BR24110, RB24110, and RR6110. Figure 3, 4 total equals 56 plus 24 plus 24 plus 6, 110, equals 110, 110 equals 1. Note, if you draw a red on the first draw from the 3 red possibilities, there are 2 red marbles left to draw on the second draw. You do not put back or replace the first marble after you have drawn it. You draw without replacement so that on the second draw there are 10 marbles left in the urn. Calculate the following probabilities using the tree diagram. Problem APRR equals solution APRR equals 311, 210 equals 6, 110. Problem B. Fill in the blanks. Letter 1D443, letter 1D445, letter 1D435, letter 1D435, letter 1D445. 311, 810 plus equals 48, 110. Solution B. Letter 1D443, letter 1D445, letter 1D435, letter 1D435, letter 1D445. 311, 810 plus 811 is 310 equals 48, 110. Problem C. PR on second, B on first equals solution C. PR on second, B on first equals 310. Problem D. Fill in the blanks. Letter 1D443, letter 1D445 on first, letter 1D435 on 2D equals 24, 110. Solution D. Letter 1D443, letter 1D445 on first, letter 1D435 on 2D equals 311, 810 equals 24, 110. Problem E. Find PBB. Solution E. PBB equals 811, 710. Problem F. Find PB on second, R on first. Solution F using the tree diagram PB on second R on first, PRB equals 810. If we are using probabilities, we can label the tree in the following general way. This is a tree diagram for a two-step experiment. The first branch shows first outcome, PB and PR. The second branch has a set of two lines for each line of the first branch. The probability of B given B equals PBB. The probability of R given B equals PRB. The probability of B given R equals PBR. And the probability of R given R equals PRR. PRR here means PR on second R on first, PBR here means PB on second R on first, PRB here means PR on second B on first, PBB here means PB on second B on first. Try it 3. 25 in a standard deck there are 52 cards, 12 cards are face cards F and 40 cards are not face cards N. Draw 2 cards one at a time without replacement. The tree diagram is labeled with all possible probabilities. This is a tree diagram with branches showing frequencies of each draw. The first branch shows two lines, F1252 and N4052. The second branch has a set of two lines, F1152 and N4051, for each line of the first branch. Multiply along each line to find FF121 2652, FN480 2652, NF480 2652, and NN1560 2652. Figure 3-5 find letter 1D443, letter 1D439, letter 1D441, letter 1D441, letter 1D439. Find P, NF. Find P at most one face card. Hint. At most one face card means 0 or one face card. Find P at least one face card. Hint. At least one face card means one or two face cards. Example 3. 26. A litter of kittens available for adoption at the Humane Society has 4 tabby kittens and 5 black kittens. A family comes in and randomly selects 2 kittens without replacement for adoption. This is a tree diagram with branches showing probabilities of kitten choices. The first branch shows 2 lines, T49 and B59. The second branch has a set of 2 lines for each first branch line. Below T49 are T38 and B58. Below B59 are T48 and B48. Multiply along each line to find probabilities of possible combinations. Problem: what is the probability that both kittens are tabby? A12, 12B, 49s, 49C, 49s, 38D, 49s, 59. What is the probability that one kitten of each coloring is selected? A49, 59B, 49, 58C, 49, 59 plus 59, 49D, 49, 58 plus 59, 48. What is the probability that a tabby is chosen as the second kitten when a black kitten was chosen as the first? What is the probability of choosing 2 kittens of the same color? Solution A, C, B, D, C48, D3272. Try it 3. 26. Suppose there are 4 red balls and 3 yellow balls in a box. 2 balls are drawn from the box without replacement. What is the probability that 1 ball of each coloring is selected? A Venn diagram is a picture that represents the outcomes of an experiment. It generally consists of a box that represents the sample space S together with circles or ovals. The circles or ovals represent events. Venn diagrams also help us to convert common English words into mathematical terms that help add precision. Venn diagrams are named for their inventor, John Venn, a mathematics professor at Cambridge and an Anglican minister. His main work was conducted during the late 1870s and gave rise to a whole branch of mathematics and a new way to approach issues of logic. We will develop the probability rules just covered using this powerful way to demonstrate the probability postulates, including the addition rule, multiplication rule, complement rule, independence, and conditional probability. Example 3, 27. Suppose an experiment has the outcomes 1, 2, 3, 12 where each outcome has an equal chance of occurring. Let event A equals 1, 2, 3, 4, 5, 6, and event B equals 6, 7, 8, 9. Then a intersect B equals A equals 6, and a union B equals A letter 1 D435 equals 123,456,789. The Venn diagram is as follows. A Venn diagram. An oval representing set A contains the values 1, 2, 3, 4, 5, and 6. An oval representing set B also contains the 6, along with 7, 8, and 9. The values 10, 11, and 12 are present but not contained in either set. Figure 3-6. Figure 3-6 shows the most basic relationship among these numbers. First, the numbers are in groups called sets, set A and set B. Some number are in both sets. We say in set A and set B. The English word and means inclusive, meaning having the characteristics of both A and B, or in this case, being a part of both A and B. This condition is called the intersection of the two sets. All members that are part of both sets constitute the intersection of the two sets. The intersection is written as A letter 1 D435, where is the mathematical symbol for intersection. The statement A letter 1 D435 is read as A intersect B. You can remember this by thinking of the intersection of two streets. There are also those numbers that form a group that, For membership, the number must be in either one or the other group. The number does not have to be in both groups, but instead only in either one of the two. These numbers are called the union of the two sets, and in this case they are the numbers 1, 5 from exclusively, 7, 9 from set B exclusively, and also 6, which is in both sets A and B. The symbol for the union is, thus, a letter 1D435 equals numbers 1, 9, but excludes number 10, 11, and 12. The values 10, 11, and 12 are part of the universe, but are not in either of the two sets. Translating the English word "and" into the mathematical logic symbol, intersection, and the word "or" into the mathematical symbol, union, provides a very precise way to discuss the issues of probability and logic. The general terminology for the three areas of the Venn diagram in Figure 3.6 is shown in Figure 3.7. Try it 3. 27. Suppose an experiment has outcomes black, white, red, orange, yellow, green, blue, and purple, where each outcome has an equal chance of occurring. Let event C equals green, blue, purple, and event P equals red, yellow, blue. Then C letter 1D443 equals blue, and C letter 1D443 equals green, blue, purple, red, yellow. Draw a Venn diagram representing this situation. Example 3, 28. Flip two fair coins. Let A equals tails on the first coin. Let B equals tails on the second coin. Then A equals TTTH and B equals TTHT. Therefore A equals TT. A letter 1D435 equals THTTHT. The sample space when you flip two fair coins is X equals HH, HT, TH, TT. The outcome HH is in neither A nor B. The Venn diagram is as follows. This is a Venn diagram. An oval representing set A contains tails plus heads and tails plus tails. An oval representing set B also contains tails plus tails, along with heads plus tails. The universe S contains heads plus heads, but this value is not contained in either set A or B. Figure 3.7. Try it 328. Roll a fair six-sided die. Let A equals a prime number of dots is rolled. Let B equals an odd number of dots is rolled. Then A equals 2, 3, 5 and B equals 1, 3, 5. Therefore A equals 35. A letter 1D435 equals 1235. The sample space for rolling a fair die is S equals 1, 2, 3, 4, 5, 6. Draw a Venn diagram representing this situation. Example 329. Problem: a person with type O blood and a negative Rh factor Rh can donate blood to any person with any blood type. 4% of African Americans have type O blood and a negative Rh factor. 5–10% of African Americans have the Rh factor, and 51% have type O blood. This is an empty Venn diagram showing two overlapping circles. The left circle is labeled O and the right circle is labeled Rh. Figure 3.8. The O circle represents the African Americans with type O blood. The Rh oval represents the African Americans with the Rh factor. We will take the average of 5% and 10% and use 75% as the percent of African Americans who have the Rh factor. Let O equals African American with type O blood and R equals African American with Rh factor. R equals letter 1D443, letter 1D442, equals letter 1D443, letter 1D442, letter 1D445. Equals in the Venn diagram, describe the overlapping area using a complete sentence. In the Venn diagram, describe the area in the rectangle but outside both the circle and the oval using a complete sentence. Solution: A051, B0, 75, C04, D0. 545. E. The area represents the African Americans that have type O blood and the Rh factor. F. The area represents the African Americans that have neither type O blood nor the Rh factor. Try it 3. 29. Roll a fair six-sided die. Let A equals a prime number of dots is rolled. Let B equals an odd number of dots is rolled. Then A equals 2, 3, 5 and B equals 1, 3, 5. Therefore A and B equals 3, 5. Or B equals 1, 2, 3, 5. The sample space for rolling a fair die is S equals 1, 2, 3, 4, 5, 6. Draw a Venn diagram representing this situation. Example 3. 30–40% of the students at a local college belong to a club and 50% work part-time. 5% of the students work part-time and belong to a club. Draw a Venn diagram showing the relationships. Let C equals student belongs to a club and PT equals student works part-time. This is a Venn diagram with one set containing students in clubs and another set containing students working part-time. Both sets share students who are members of clubs and also work part-time. The universe is labeled S. Figure 3. 9. If a student is selected at random, find the probability that the student belongs to a club. PC equals 0. 40. The probability that the student works part-time. PPT equals 0. 50. The probability that the student belongs to a club and works part-time. PT equals 0. 5. The probability that the student belongs to a club given that the student works part-time. Letter 1D443. Letter 1 D436, letter 1 D443, letter 1 D447 equals letter 1 D443. Letter 1 D436, letter 1 D443, letter 1 D447, letter 1 D443, letter 1 D443, letter 1 D447 equals 0. 50 equals 0. 1. The probability that the student belongs to a club or works part-time. Letter 1 D443, letter 1 D436 PT equals letter 1 D443, letter 1 D436 plus letter 1 D443 PT minus letter 1 D443, letter 1 D436 PT equals 0. 40 plus 0, 50 minus 0. 5 equals 0. 85. In order to solve example 330, we had to draw upon the concept of conditional probability from the previous section. There we used tree diagrams to track the changes in the probabilities, because the sample space changed as we drew without replacement. In short, conditional probability is the chance that something will happen given that some other event has already happened. Put another way, the probability that something will happen conditioned upon the situation that something else is also true. In example 330, the probability P CPT is the conditional probability that the randomly drawn student is a member of the club, conditioned upon the fact that the student also is working part-time. This allows us to see the relationship between Venn diagrams and the probability postulates. Try at 330. 50% of the workers at a factory work a second job, 25% have a spouse who also works, 5% work a second job and have a spouse who also works. Draw a Venn diagram showing the relationships. Let W equals works a second job and S equals spouse also works. In a bookstore, the probability that the customer buys a novel is 0. 6. And the probability that the customer buys a nonfiction book is 0. 4. Suppose that the probability that the customer buys both is 0. 2. Draw a Venn diagram representing the situation. Find the probability that the customer buys either a novel or a nonfiction book. In the Venn diagram, describe the overlapping area using a complete sentence. Suppose that some customers buy only compact discs. Draw an oval in your Venn diagram representing this event. Example 331. A set of 20 German Shepherd dogs is observed. 12 are male, 8 are female, 10 have some brown coloring, and 5 have some white sections of fur. Answer the following using Venn diagrams. Problem: draw a Venn diagram simply showing the sets of male and female dogs. Solution: the Venn diagram below demonstrates the situation of mutually exclusive events where the outcomes are independent events. If a dog cannot be both male and female, then there is no intersection. Being male precludes being female, and being female precludes being male. In this case, the characteristic gender is therefore mutually exclusive. A Venn diagram shows this as two sets with no intersection. The intersection is said to be the null set using the mathematical symbol. This is a Venn diagram, two circles inside a rectangle. The circles do not intersect or overlap. One circle is labeled male, the other circle is labeled female. Figure 310. Problem: draw a second Venn diagram illustrating that 10 of the male dogs have brown coloring. Solution: the Venn diagram below shows the overlap between male and brown where the number 10 is placed in it. This represents male brown, both male and brown. This is the intersection of these two characteristics. To get the union of male and brown, then it is simply the two circled areas minus the overlap. In proper terms, male brown equals male plus brown minus male brown will give us the number of dogs in the union of these two sets. If we did not subtract the intersection, we would have double counted some of the dogs. This is a Venn diagram, two overlapping circles inside a rectangle. The left circle is labeled male, the right circle is labeled brown. The overlapping section shows the number 10. Figure 311. Problem: now draw a situation depicting a scenario in which the non-shaded region represents no white fur in female or white fur female. The prime above fur indicates not white fur. The prime above a set means not in that set, e.g. a means not a. Sometimes the notation used is a line above the letter. For example, a equals. Solution: this is a Venn diagram, two overlapping circles inside a rectangle. The left circle is labeled female. The right circle is labeled white fur. The section of the left female circle that lies outside the white fur circle is shaded. Figure 312. The addition rule of probability. We met the addition rule earlier, but without the help of Venn diagrams. Venn diagrams help visualize the counting process that is inherent in the calculation of probability. To restate the addition rule of probability, letter 1D443, letter 1D434, letter 1D435 equals letter 1D443, plus letter 1D443, letter 1D435 minus letter 1D443, letter 1D434, letter 1D435. Remember that probability is simply the proportion of the objects we are interested in relative to the total number of objects. This is why we can see the usefulness of the Venn diagrams. Example 331 shows how we can use Venn diagrams to count the number of dogs in the union of brown and male by reminding us to subtract the intersection of brown and male. We can see the effect of this directly on probabilities in the addition rule. Try it: a set of 40 people are selected randomly. 24 are male, 16 are female, 21 like coffee, and 19 like tea. Answer the following using Venn diagrams. Draw a Venn diagram simply showing the sets of male and female. Draw a second Venn diagram illustrating 14 males liking coffee. Draw a situation with a region depicting female and not liking tea. Example 332. Let's sample 50 students who are in a statistics class. 20 are first-year students and 30 are sophomores. 15 students get a B in the course, and 5 students both get a B and are first-year students. Problem: find the probability of selecting a student who either earns a B or is a first-year student. We are translating the word "or" to the mathematical symbol for the addition rule, which is the union of the two sets. Solution: we know that there are 50 students in our sample, so we know the denominator of our fraction to give us probability. We need only to find the number of students that meet the characteristics we are interested in, i.e. any first-year students and any student who earned a grade of B. With the addition rule of probability, we can skip directly to probabilities. Let A equals the number of first-year students, and let B equals the grade of B. Below we can see the process for using Venn diagrams to solve this. The letter 1d443, letter 1d434 equals 2050 equals 0. 40, letter 1d443, letter 1d435 equals 1550 equals 0. 30 and letter 1d443, letter 1d434, letter 1d435 equals 550 equals 0. 10, therefore letter 1d443, letter 1d434, letter 1d435 equals 0. 40 plus 0, 30 minus 0, 10 equals 0, 60. Venn diagrams model the formula for P, A, and B. The first Venn diagram shows two overlapping circles inside a rectangle. The left circle is labeled A, the right circle is labeled B, and the overlapping section is labeled A intersect B. This diagram is labeled P, A union B. After this diagram is an equal sign. Below the first diagram is a series of diagrams. Each shows the same arrangement, overlapping circles A and B. The first diagram shows circle A completely shaded. The second diagram shows circle B completely shaded. The third diagram shows the overlapping portion of circles A and B shaded. The expression is first diagram plus second diagram, third diagram, figure 3. 13. If two events are mutually exclusive, then, like the example where we diagram the male and female dogs, the addition rule is simplified to just letter 1d443, letter 1d434, letter 1d435, equals letter 1d443, a letter 1d443, letter 1d435 minus 0. This is true because, as we saw earlier, the union of mutually exclusive events is the null set. The diagrams below demonstrate this. Venn diagrams model the formula for P, A, and B in the special case where A and B do not overlap. P, A union B is represented by two separate non-overlapping circles inside a rectangle. The left circle is labeled male. The right circle is labeled female. To the right of this diagram is an equal sign. A sum of diagrams is on the line below. The left diagram shows only the male circle inside the rectangle and is labeled P, A. Between the diagrams is a plus sign. The right diagram shows only the female circle inside the rectangle and is labeled PB. Figure 314. Try it. 3. 32. A set of 40 random people is taken. 15 are male and 25 are female. 18 people like coffee. 10 people are male and like coffee. Find the probability of selecting a person that likes coffee or is male. The multiplication rule of probability. Restating the multiplication rule of probability using the notation of Venn diagrams we have. Letter 1d443, letter 1d434, letter 1d435 equals letter 1d443, letter 1d434, letter 1d435, letter 1d443, letter 1d435. The multiplication rule can be modified with a bit of algebra into the following conditional rule. Then Venn diagrams can then be used to demonstrate the process. The conditional rule, letter 1d443, letter 1d434, letter 1d435, equals letter 1d443, letter 1d434, letter 1d435, letter 1d443, letter 1d435, using the same facts from example 3. 32 above, find the probability that someone will earn a B if they are first-year students. Letter 1d443, letter 1d434, letter 1d435 equals 0, 10, 0. 30 equals 1, 3. Venn diagrams model the formula for P, A given B. The diagrams used show overlapping circles A on the left and B on the right inside a rectangle. The equation is PAB equals Venn diagram showing PA intersect B, as the shaded section where left circle A intersects right circle B divided by Venn diagram showing PB by shading right circle B completely. Figure 315, the multiplication rule must also be altered if the two events are independent. Independent events are defined as a situation where the conditional probability is simply the probability of the event of interest. Formally, independence of events is defined as letter 1d443, letter 1d434, letter 1d435, equals letter 1d443, letter 1d434, or letter 1d443, letter 1d435, letter 1d434, equals letter 1d443, letter 1d435. When flipping coins, the outcome of the second flip is independent of the outcome of the first flip. Coins do not have memory. The multiplication rule of probability for independent events thus becomes letter 1d443, letter 1d434, letter 1d435, equals letter 1d443, letter 1d434, letter 1d443, letter 1d435. One easy way to remember this is to consider what we mean by the word and. We see that the multiplication rule has translated the word and to the Venn notation for intersection. Therefore, the outcome must meet the two conditions of first year and grade of B in the above example. It is harder, less probable to meet two conditions than just one or some other one. We can attempt to see the logic of the multiplication rule of probability due to the fact that fractions multiplied times each other become smaller. The development of the rules of probability with the use of Venn diagrams can be shown to help as we wish to calculate probabilities from data arranged in a contingency table. Example 3, 33 Table 3. 13 is from a sample of 200 people who were asked how much education they completed. The columns represent the highest education they completed, and the rows separate the individuals by men and women. Less than high school, some college, grad, total men, 5, 15, 40, 60, 120. Women 8, 12, 30, 30, 80 total, 13, 27, 70, 90, 200 Table 3. 13 Now, we can use this table to answer probability questions. The following examples are designed to help understand the format above while connecting the knowledge to both Venn diagrams and the probability rules. Problem: what is the probability that a selected person both finished college and is a woman? Solution: this is a simple task of finding the value where the two characteristics intersect on the table, and then applying the postulate of probability, which states that the probability of an event is the proportion of outcomes that match the event in which we are interested as a proportion of all total possible outcomes. P college grad female equals 30, 200 equals 0. 15 Problem: what is the probability of selecting either a woman or someone who finished college? Solution: this task involves the use of the addition rule to solve for this probability. P college grad female equals PF PCG minus PFCG. P college grad female equals 80 200 plus 90 200 minus 30 200 equals 140 200 equals 0. 70 Problem: what is the probability of selecting a high school graduate if we only select from the group of men? Solution: here we must use the conditional probability rule, the modified multiplication rule, to solve for this probability. PHS grad man equals letter 1d443, HS grad man P man 15 200, 120 200 equals 15 120 equals 0. 125 Problem: can we conclude that the level of education attained by these 200 people is independent of the gender of the person? Solution: there are two ways to approach this test. The first method seeks to test if the intersection of two events equals the product of the events separately, remembering that if two events are independent, then PA asterisk P B equals PAB. For simplicity's sake, we can use calculated values from above. Does P college grad woman equals PCG PF 30 200 not equal to 90 200 80 200 because 0. 15 not equal to 0 18. Therefore, gender and education here are not independent. The second method is to test if the conditional probability of a given B is equal to the probability of A. Again, for simplicity, we can use an already calculated value from above. Does PHS grad man equals PHS grad 15 120 not equal to 27 200 because 0. 125 not equal to 0 135. Therefore, again, gender and education here are not independent. Try it 3. 33 The table shows a spread of what 100 random people like to eat. The columns represent the fruit that they like to eat, and the rows separate the individuals by men and women. Grape, watermelon, apple, pomegranate. Total men 12 18 20 10 60. Women 13 7 15 5 40. Total 25 25 35 15 100. Table 3. 14 Answer the following questions. What is the probability that a selected person likes pomegranate and is a man? What is the probability of selecting either a man or someone who likes apple? What is the probability of selecting a person who likes watermelon if we select from the group of women?